Me to this workshop. First, excuse me because my English is not so perfect. I didn't have the time to train in the pub yesterday because I didn't went to the pub. This work is in fact a joint work with two other guys from Cambridge University. In fact, Arnaud Doucet was there in the electrical engineering department some years ago. Now he's in UBC Vancouver. And Summit Singh, which is just behind you here. So if you have questions about this talk, you can ask Summit about some application areas and some theoretical computation of some extensions. So I've seen that many people were looking at some partial differential equations. So basically, I will treat only discrete time generation models. But to introduce you to continuous time versions, I will make a short presentation on the blackboard to see the connection between PDEs and this type of models. So let's just start to say that, for example, if you have a generator like that, minus VT, so here may be a Laplacian, for example, and here a potential function. And you look at, in the weak sense, at the evolution. So, okay, for me, gamma t of f will be the integral with respect to a function of the measure gamma. And I'm looking at the evolution of gamma t and gamma t over dt.
Sorry.
Yes.
Can you turn your microphone on?
Okay. Thanks. Okay, it's better. So I'm looking at this type of evolution. So gamma t of L G T of f. So here you have, for example, the Laplacian minus some multiplication here. So if you look at this type of weak type solution of PDEs, then you end up with a solution which is given by a Feynman-Kac formula. I don't know if I have the place here. Okay, we write in small. The integral from 0 to t vs xs ds. So in fact, I will be interested, you will see, in this type of formulas which are defined for any function f, and this type of quantities satisfy this type of evolution equations. And you see that, for example, for this type of evolution equation to have a solution, you need to choose the test function in the domain of the generator. So these equations are, let's say, in a sense, need some regularity on the function, while these expressions, which are the solution, are defined for any function, for indicator type function, for example. Another type of model I will look is the normalized equations. So gamma t is gamma t of f divided by gamma t of 1. So this one will correspond, in a sense, to Zakai type equations. So I forgot a t here, sorry. And this type, so these are positive measures. So if I divide by the total mass, I end up with a probability measure, and I can look at the evolution of these equations. And the evolution of these equations are defined in the same way. So I don't have the room to do that, so I will just do it here. So eta t of f. And here you will have some generator, t eta t. That depends on the current distribution at that time, and these generators are defined like that. So you take, for example, the Laplacian, and you had here a jump type generator of that form, eta dy. So what is the interpretation of this type of equation is eta t is the law of some Markov process, x bar. X bar as this type of generator means that it evolves according to mutation, exploration, like with LT, for example. If it's a Laplacian, you will have diffusion evolutions. And as at that rate, sorry again, at that rate, it jumps from its location to a new position, randomly chosen according to its current distribution. Okay, so in fact, if you normalize the Feynman-Kac models, like in filtering and so on, you obtain the law of a Markov chain, which is unfortunately nonlinear, in a sense that it jumps from time to time at some given rate from one location to another one, randomly chosen according to this one. Okay, so now to get a little further, what I said is that these equations, gamma t was satisfied the Feynman-Kac model, and you can see that these, sorry, okay, 1 over zt, the exponential 0t vs xs ds dpt. So this is the law of the process whose infinitesimal generator is LT. For example, if you have diffusion Laplacian, this will be the Wiener measure of the Wiener process from 0 to t. So you normalize and you have this type of measures. And if you look at the marginal at time t marginals, they are equal to eta t. Okay? So during the talk, I will be interested in the discrete time version of these measures. So I want to compute not only eta t, not only gamma t, but also these complete measures in the full path space. Okay? So you may ask, what is the connection between this and filtering? So now if you replace this by by this one, from 0 to t, h xs dy 1/2 0 to t h xs square ds, then in this situation, you obtain the so-called Kallian-Pourch-Tribel formula. If you integrate q with respect to a function of the signal process from 0 to t, you obtain the Kallian-Pourch-Tribel formula. Of course, the difficulty here is that you have a stochastic integral and you don't have dt here. Okay? So now, as I said, I will consider discrete time versions. So suppose that you discretize here the time. So you will end up with some from 0 to n, or let's put this out. So some function. This can be written in terms of a product of some functions. So you can think that this is at time tp, at let's say xt, xp is in fact the value of x at time tp, and you have chosen a time steps so that you can discretize this guys or this guy and to write in that form, just using Euler approximations here and here. You obtain this type of models, and from this type of model, of course, you can write in that form. Now, if you have this type of measure in the discrete time case, if you consider, for example, xp as being another process between two times, tp and tp plus 1, for example, if the times are deterministic, this is still a Markov process. If you can also put here a random stopping time, ordered random stopping times, so that you will have a Markov process in the space of excursions. And if you take this type of potential here, for example, from time tp to time tp plus 1 vs x prime s ds, so you take the integral of this path between these two times. From this formula, you end up with this, more or less. Okay, so this discrete time model seems to come directly from a time discretization, but they can be used to represent this type of model even in continuous time, or more general models, for example, excursion-like models. Okay, so that's only to give the introduction why I will be considering discrete time models. So let me start now the talk. So first I will give you an introduction and some motivation. Some nonlinear models, because you have seen in the beginning, if I was looking at the evolution of the normalized distribution, I was ending with the law of a nonlinear Markov chain. In the discrete time case, it's a little more tricky to write, but not much. And we will end up with the Markov interpretation of this type of formulas. But it will be a nonlinear Markov interpretation in the sense that every transition depends on the law of the chain the time before. That's all. And then I will give you some convergence result without entering in any details, if you want. So it will be as usual. I think it's the second time I give this talk here, but in another place it was some months ago. So unfortunately, I will not enter into the details on this result, but we can discuss about that, or you have usually HTTP links to that, and I will show you some additive functional approximations. Okay, so let's start. So as in every French school, I start with 2 slides of notations. No, I've seen a lot of notations yesterday. So today is only 1 slide of notation. So I take a state space. P of E is the set of probabilities, easy to remember. B of E, the set of bounded functions. And instead of writing integrals, I prefer to write mu of f, the integral of f with respect to mu. If I have an integral operator, the same as I have done with generators, this integral operator acts on the right on function. So if you have a function, you act on the right, you have another function. So if m is the transition of a Markov chain, this is nothing but the mean value of the function of the next step given the past. That's all. And if it also acts on the right, on the left, sorry, on measure. So if you have a measure, mu m is the measure given by the integral of mu with respect to m. It's a linear transport equation. So in the sense that if mu is the law of a Markov process at a given time, m the transition, one way to compute the law, the next step, is to make this integral. That's all. This is the concatenation rule. And of course, by Fubini theorem, if I have mu m applied to f, I can do mf or mu m as I want. Okay. Okay. So these formulas are more or less traditional in probability, but this notation is not so used. So I will use psi g of mu as being this transformation. I take the measure mu and I multiply by some positive function in such a way that I can normalize and I stay in the set of measures. Okay, that's the only 2 notations. And you can see that all of these notations in finite state space, if you take mu, order finite state space, if you take mu as this line vector and f as the column vector, all these operations are matrix operations, vector matrix operations. So they are very convenient to work with this. Okay, so these are the discrete Feynman-Kac measures we consider today. So the Markov chain will be written xn. They will have a Markov transition written by capital M. And I will consider non-homogeneous Markov chain that can jump from one state to another, that the state space can change in time. And you will see, for example, this allows me to consider, of course, everything can be embedded in homogeneous settings, but it's not so transparent after that to see what happened. Xn may be, for example, the path of a Markov chain from 0 to time n. So the path of a Markov chain from 0 to time n, you can go to the path of the Markov chain from 0 to time n plus 1, keeping what you have done, and you just add a new move. But this is still a Markov chain. Okay, so the Feynman-Kac model is the one I have already written there. So it's nothing but the law of a free Markov chain evolution, xn, and you multiply this by a product of functions, positive functions. For example, if you take P as being the indicator functions like that, I think it's more transparent than filtering, but if you take P as the indicator function of a given set, then Qn is nothing but the law of the chain, given the fact that it was at any time in the set AP. Okay, so it's because you integrate all paths except the one who doesn't satisfy this indicator function. The other object is the n-time marginal, so I consider Qn the marginal at time n, so it's given by this, function by function. So Fn is a function, and I normalize them. And the other notation, and after I think it's finished, is Q hat, eta hat, and gamma hat, which are the same measures, except that I consider products with the last time. So it's simply a new conditioning. For example, Qn, you see the product was up to n excluded, so I didn't ask xn to be in AP. But if I put the product up to n, I will have P less or equal to n. I don't want x to be out of an. So here we are. These are the notations. Okay, so now some example. I gave already one. Now is the filtering example. So if I consider a Markov chain whose transition is given like that, xn is the signal process, yn is the observation, and basically I'm saying that xn is a Markov chain with transition m, and each time xn is somewhere, I observe it using the function g, x, y, gamma, y, dy, which is the law of the observation. So if you have a Markov chain in product space like that, given the observation sequence, you just plug in the previous formula. Gn has been this little function gn, xn, yn in the previous model, and you end up that eta hat is the law of the signal at time n, given the observations. And if you look at the normalizing constant, you end up with the density of this sequence of observations. Okay, so it's a direct application of the formula I gave before. But now if you look at the whole distribution on path space, you end up with the law of the full path of the signal given the observations. Okay, so it's a direct application. I just take Gn here equal to these so-called likelihood functions. That's all. Okay, so it's more tricky to write, but now I'm looking to something else. I take a Markov chain whose density depends on some parameter theta. I take the likelihood function that may depend on some parameter theta. So now all the objects I have defined previously depends on this parameter theta, and I'm interested, for example, in computing this derivative of all the measures I have given previously with respect to this parameter. So there are many applications of that. So if you look at the derivative of the log, you end up with a formula which says it's qn theta applied on some function of the following form, which is written there. I will not comment. And if you want to study the sensitivity of the filter with respect to the parameter theta, you take a test function phi n, and you end up with the formula in the right-hand side. So in some applications, for example, if you do expected maximization algorithms, you have this type of quantities to measure. So you have one parameter and a new one, and you want to minimize this quantity. And to do that, it's equivalent to maximize the other one. So if you do that, that's used in SAEM algorithm. So you have a parameter theta, and you look for the next one, which is the one which maximizes these quantities. And each time you need to compute the previous measure applied to additive functionals of the following form. Okay, so that's a kind of example. But if you don't like this type of example, it's no problem. Just look at, for example, if you want to compute the previous distributions here, but the test function is the sum of local function at any time. For example, you are interested, what is the average time the signal spent in a given part of the space given the observation. Okay, so I don't want to compute this law in all path space, but for particular additive functionals. So what I gave after that, these are examples where I want to compute Qn on some additive functionals like that. Okay, and this appears in parameter estimation in either Markov chain models. Okay, so now we'll give you 3 key observations which are useful after that. So the first, so I remember just in the first, the definition of eta and gamma. Just one remark, if you look in the right-hand side formula, if I take xn as being the law of a path space, in path space of an auxiliary Markov chain from 0 to time n, I just plug xn in the right-hand side there, and I obtain a very complex formula. But if g only depends on the final time, these marginal models coincide with the path space model. So in fact, we can think that these marginal models are marginal and so on. But if you consider general state spaces, they encapsulate the model in path space. Okay? Because you can consider path space models. The second important formula is this one, which is very nice for students, is to say that the mean value of a product with a Markov chain is the product of the mean values. So this is very nice. But of course, it's a different distribution. The distribution here is the normalized distribution there. So in fact, for example, if G was the indicator function, this is the probability for a Markov chain to stay in a tube very, very long time. So it's a very, very small number. And one way to approximate this very small number is to approximate these guys. So these guys are more easy to approximate than the whole ones, in a sense, intuitively. So that's why I will use this formula. If I can approximate the measure, the normalized measure eta, I will just plug here the approximation, and I will obtain an approximation of these normalized measures. Okay, and the proof of that is quite simple, because the mean value of a product, you just take one function out, and you have the mean value of the product up to one order less, the last function. You normalize, you have this, and you plug it here, and you have this product formula, which is quite simple to write. Okay, maybe in continuous time, no. Okay, the other key observation is this one. If I have a Markov transition with a given density with respect to some measure, lambda n here may be the Lebesgue measure, for example. So H is, for example, the Gaussian transitions. Okay, so that condition is satisfied in most applications. So if the Markov transition of the signal, for example, of the underlying Markov process has the following form, with some reference measure lambda, in that case, you can write the measure on path space in this backward form. So that's very interesting. You start with the law of the marginal at time n, and you do a Markov transition. Then that depends on the law at time n-1, and you go like that backward in time, up to the last time. I don't know this formula in continuous time, so that's why I've chosen to present this in discrete time. So maybe it would be interesting to discuss about that. I don't know this type of formula in continuous time. So what are these special Markov transitions? They are defined in that way. This is the proportional sign. So you just multiply the density of M by the function g, and of course you integrate with respect to this measure on these two parameters. So this is this divided by the integral of the numerator with respect to this, and the measure eta. Okay? So this is a strange formula, but I really like this formula. It has a nice feature. And of course, one way to approximate these quantities will be, if I can approximate the measure eta here, it's to replace everywhere eta by the approximated measures. So if eta are discrete supported measures, you will see that eta n is a discrete supported measure. M will become a matrix, because this will be discretely supported, and on this, which is on the previous support. So this will be a matrix, and so on and so on. Okay, so now I start. So now something which is very important is to look at the normalized measure, how they evolve in time. So as in filtering, we have two evolutions. The first one, it's called the updating or the correction. So remember, psi g is the multiplication of the measure by g. Very simple. You multiply eta by g. So you have eta n, for example, the law of the signal up to time n-1, and you want the law of the signal up to time n now. So you just multiply by the likelihood function at that time. Okay, so that's the updating transition. In Kalman filter, is also called the updating. You have prediction, updating, but it's the same formula, but in terms of Gaussian measures. So here we don't have Gaussian measure, but we have the same rule. You multiply the measure by some potential function. And the second step is a prediction step, a Markov transport, a very simple Markov transport. You have the updated measure and you predict, so you integrate with the transition of the chain from n to n+1 before the new observation arrives. Okay? So if you look at the normalized measure, they satisfy a nonlinear equation, which is given by these two transport transitions. So now something which is quite important is to look at the multiplication operator, which can be written in terms of a transport equation. So remember that if I have a Markov transition, it acts on the left, so that to create a new measure. So here the multiplication is written as the law at hand. You integrate with the Markov transition, which is given there. So the Markov transition said, with this probability, you stay where you are, and with this probability, you jump to a new location randomly chosen according to these distributions. Okay? So I have succeeded to write the transition from n to n plus 1 as a nonlinear transport and a linear transport. So if I write this in that form, I have the law of Markov chain whose transition depends on the current distribution. So this is the simple way to write these recursions. So that's what I've written there. If we have constructed a nonlinear Markov chain. So eta n is the law of the nonlinear Markov chain x bar, which can be thought as a perfect sampling algorithm. If you can sample this algorithm, that means that at any time the law of the chain equals to eta n. So for example, in filtering, this gives an interpretation of the law of conditional distribution in terms of the law of the Markov process. So if you can sample this Markov process, you have succeeded to sample the conditional distribution. And you have succeeded to make Monte Carlo approximation of PDEs and so on. So now let's look at the evolution of its distribution is written in the following form with a transition that depends on the current distribution. You have the selection transition and the mutation transition. So now if you look at the local transition of that chain, of course, you go from one state to another, sampling this transition that depends on the previous distribution. And we can see this type of model in physics, for example. If you look at the particle interpretation of fluid mechanics, you have the evolution of the position which is given by the velocity of the particle, and the velocity of the particle which depends on the distributions of the other velocity of particles around it. Okay, so it's the same type of model. You have an evolution equation that depends on the current distribution at that time. Okay, so now an important object which is not possible to write in the following form in continuous time, but which can be exhibited by fixed point techniques, is the law of this Markov chain from 0 to time n. You start with the initial distribution, you sample a transition that depends on eta naught, and so on, and you sample the transition at time n that depends on this one, but to compute this one, you need to compute these integrations. So it's a very complex model to solve, but quite general. Okay, so now how to sample according to this transition? To sample this transition is, as I said, if you try to sample this, we have an explicit expression, but if you can try to sample that, you need to compute these measures. Okay, so the idea of mean field particle approximations is to say, okay, I will run a population of individuals, and each population give me at any time an approximation of the law at that time. Okay, so suppose you have a population of individuals such that the occupation measure of these individuals approximate the desired solution. Suppose we have that at that time. So instead of sampling the transition with the limiting distribution, I just plug here the empirical measure at that time, which is by condition, by assumption, an approximation. So in a schematic picture, this is how it works. You sample not the transition of the perfect chain, of course. You cannot compute the law at that time. But if at a given time n, eta capital N is an approximation of that law, you replace the desired limiting transition by this one, where you just replace eta n by eta capital N, which is an approximation. Okay, and if you do that, you have almost IID sample of the Markov chain, of the desired Markov chain. Because that's typical in a Makin-Vlasov equation in continuous time. You have a diffusion equation with a drift term, and this drift term depends on the law of this process. So what you do in particle methods, you say, okay, each particle evolves with this drift term, but instead of the law, I plug the empirical measure. That's all. So it's the same the same line of ideas. And something we can prove is that the occupation measure of the whole system converges to the Makin distribution. Okay, so what are some key advantages of these techniques? The first one is, remember what we have done. Each transition is sampled according to the Markov kernel K that depends on the law at that time. So if you look at the mean value of each particle given that time, you end up with the transport equation in the right-hand side. So the occupation measure at time n, up to some randomness, satisfy in the mean the evolution of the limiting model, plus some perturbation term, which is 1 square root of n, w and n. And the definition of that term is simple, is given by this formula. So you have the empirical measure minus its mean multiplied by square root of n. So it's a total definition here. Okay? So, but written in that way, you can see that in the mean you satisfy the evolution equation plus some fluctuation term of order 1 square root of n, which only comes from the fact that you have done some samples. Okay? So if you look at that, and okay, something we can prove that is that all these w's from 0 to n, if you look at the vector or this big matrix, you converge in the limit to some independent centered Gaussian fields. So in a sense, you solve the system with some order 1 square root of n perturbation, and each time you add, let's say, a Gaussian, a little Gaussian, and of order 1 square root of n. So if you think in terms of dynamical system, you are solving exactly the dynamical system, but from time to time, not at any time. At any time, you perturb the system. At any time, you make a perturbation of order 1 square root of n times a Gaussian. So each time, bam, bam, bam. So, but if the system is, in a sense, stable, this local perturbation will not propagate. And because they are of order 1 square root of n, you will end up with some total control of this perturbation uniformly in time, and that doesn't depend on the time parameter, and of order 1 square root of n, of course. Okay, so the idea is this one. Using this particle method, you can think these particle models in terms of stochastic perturbation of a stable dynamical system. And of course, if the system is unstable, it's impossible to have uniform convergence result because the error will propagate. So to get some intuition, I think it's a good way to look at this. Another advantage is that you don't need burning to, like if you use MCMC models. MCMC model consider, for example, that eta at time n, for example, these guys, are the invariant measure of a Markov chain. So you run the Markov chain, you wait a long time, and at some point, all the visited samples are almost distributed according to the Desiree distribution. This is the MCMC type technique. But if you change a little the distribution, for example, you add a new observation, you need to change completely the Markov chain and to start and wait a little. Okay, so here the idea is totally different. You replace, in a sense, the time dependency by the spatial dependency, and you just run the law, you just propagate the law of large number. So you get another type of approximation which is better, easier to control. The other thing which will become clearer in a few minutes is that when we run this particle approximation, for example in filtering, we will, in a sense, this will be clearer in a few minutes, we will, in a sense, refine the grid, refine the places where the observation arrives. So when you have an observation and the observation puts some mass where the distribution, conditional distribution is, so you tend to duplicate the particle in that place. So in a sense, it's like, for example, in fluid mechanics, it's the same. You represent the evolution of the velocities depending on the velocity of the particle around. So in a sense, you have a stochastic adaptive grid approximation because you follow where the probability density of the mass. The other observation is that we have a nonlinear system and we have not done any kind of linearization except this type of linearization, but we have not used any kind of approximation of k and eta n. If k depends on the complicated way of eta, no matter, we just replace eta by the occupation measure. There is no approximation. So we are completely using the nonlinearity of the system. And of course, as you will see in a few minutes, it's very simple to sample according to that. So here is, if I just plug this approximation to the Feynman-Kac to the Feynman-Kac distribution, I end up with this. So I end up with the genetic type stochastic algorithm with two steps. The first step gives how one population gives a new population, and the second step just says that each particle evolves according to the Markov transition. So these independent moves, each one moves independently. So how is defined the selection transition? So it's an acceptance rejection selection. With this probability, the particle stays in its location. And with this probability, the particle jumps to a new location, maybe itself, randomly chosen according to these distributions. Okay, so it's very simple to sample. You accept or you reject. If you reject, you jump to a new guy which is better than you, in a sense. So suppose, for example, G are the indicator function, take epsilon equal to 1. If you are in the desired set, you accept, perfect sampling. If you are not in the desired set, okay, you choose a guy which is in the desired set uniformly. Because these guys are an approximation of the law given that even. Okay. So here I will give you some approximation models. So first I've run in the first schema figure the particle model with 3 particles. So in the beginning you have 3 guys, they evolve, and the first and the last one are not selected, but they jump in the middle, both of them. From the middle they explore the space independently. Then the guy in the middle is in the wrong place, so is not accepted. So he jumps, for example, on the third guy, and from that place they evolve. Okay, so you can see the selection and mutation in this picture. So if you look, you have the current population, which are the red points, and the current population is an approximation of the n-time marginal. Okay, that's one object. The second object is the genealogical tree, which is represented with the blue line, blue points. So you have the first line, the second ancestral line, and the third ancestral line. So each ancestral line is a vector. So I look at the empirical measure of the ancestral lines, and I approximate the law, the Feynman-Kac distribution in path space. For example, this one, if I take indicator functions. Another quantity, remember that each time we make exploration and then we accept or reject. So each time I have a given proportion of individuals, in a sense, that satisfy the criteria. So if you make the product, for example, if you take here the indicator function, this will be the proportion of success of points in the set. So if you make the product of the proportion of success, you have an approximation of the product of the limiting proportion of success, which is the probability to enter in the next given the past. So this very strange formula, in fact, give you an approximation of the unnormalized, give you an approximation of the normalizing constant, and in fact they are unbiased. If you take the mean value of that, it's equal to that. So that's strange, but it's related to some martingale properties. Okay, let's see another one. You have the complete genealogical tree, which is represented with the black dots, which is all the individual at the final time, the individual at the time before, the individual at the second time, and the individual at the first time. So everyone. So I'm even considering ancestor which have not given nice offsprings, in a sense. So I'm considering everything. All the individuals at time 0, all the individuals at time 1, and all the individuals at time n. So it's the full tree. If I look at the occupation of that, measure of that, I approximate the Makin measures. Then of course the choice of K1 eta is not unique. As I said previously, it was depending on some parameter, for example epsilon, which may be taken equal to 0. But all the algorithms converge to the same marginal, but they are distinguished if you look at the full complete genealogical tree structure, which converges to the law of the nonlinear Markov chain, underlying Markov chain. Now if you remember the backward representation of this formula, which was the final one, the transition from n to n-1, depending on the law at time n-1, I plug here the occupation measures, and I have, of course, an approximation of these quantities. That's quite simple. Now, how they converge, what is the precision of these models, that will be the second part of the talk. So just to go very quickly, all of these models are not new. They are known since the beginning of the 50s. I think they start in the literature on physics. They are called diffusion Monte Carlo, quantum Monte Carlo, genetic algorithm. So I give here a panel of names, but all of these models are not new. They are used in physics. What is new, in fact, is their analysis, their stochastic analysis. So this is, as I said, the second part of the talk. So now let's look at some results on the time marginal. So the time marginal is eta n, capital N, so at the given time. So we have this type of result, and of course, with respect to the time parameter, means that the system, the underlying limiting system is stable. If the system is unstable, I cannot guarantee any of these uniform result with respect to a time parameter. It's impossible. But if the system is stable, we have this type of result. So you can read the norm with f is the supremum with respect to a countable collection of functions. We have concentration type inequalities, uniform in time. If you look at the worst error, epsilon error you can do at a given time, for no matter the time, it's a sub-Gaussian inequality of that form. So these results were done, we have done this result with Alice Guillonnet in 01, with Michel Ledoux 10 years ago, and with Emmanuel Rio in a recent paper, we have succeeded to look at Bernstein and Hofding type inequality for this type of models. And something which is related to Istvan talk yesterday is that we have some kind of Taylor expansion here, with signet measures here, which can be explicitly expressed, but this signet measure doesn't depend on the precision. So, but here you see it's the law of Q particles among capital N, so a block of particles. So of course this corresponds to the bias. So we can reduce the bias, mixing, we take, I don't know, two times the number of particles and we subtract something, and we reduce the bias. And we can reduce the bias as much as we want, but we are still bias simulation approximation models. And we can control, of course, the norm in total variation of these distributions. Okay, that's another type of result we have obtained on a normalized model, because if you remember in the beginning, the Feynman-Kac formula, there are some normalizing constants and there are also the unnormalized measures. So this will be, for example, the discrete time version approximation of the Sakai equation. So because we can compute an approximation of the normalizing constant, I just multiply the normalized one by the normalizing constant. So that simplifies, of course. So eta times the normalizing constant is gamma. So this is a natural approximation. And the point that this complex formula is unbiased. If you take the mean, you have the exact model. So we have done a lot of results on that, like fluctuation and deviation with Alice, Miklo, and Don. But we have more recently done some non-asymptotic theory, looking at the bias and the variance estimate. Something interesting is that we have a Taylor type expansion here. In fact, a polynomial expansion is stopped at finite rank. And we have explicit expression of these measures. And this is a little more recent, is to say, okay, we can, for example, if you take the test function equal to 1, this is the normalizing constant. We can approximate the normalizing constant of that order, but here we have the square. So typically, these are very small numbers, and if they are very small, these have to be very small. So in a sense, you need to divide this one by this, so this term disappears, and of course, we have an order that increases with respect to time, but it's not exponential at least. Okay, and for additive functional, so I remember you the model. I have a Feynman-Kac model in past space. I make the hypothesis that the transition have a density with respect to Lebesgue measure, for example. So I can write Q in terms of the backward Feynman-Kac, backward Markov chain that use the marginal of this distribution. This backward transition are given like that, up to some constant. And I just plug here each time I have eta n, I just plug the occupation measure. So in that case, you have only matrices, I remember. So if we, okay, I pass with that. So if we take additive functional of the following form, and I compare the approximative measure with the real one on this type of additive functional, we have obtained this kind of variance estimate. And you can see we have a bias term which comes from the fact that we are considering normalized additive functional. It's a bias term, plus 1 over n term here. So in a sense, you see that the variance is of order 1 over n square. Okay, so I think that's very strange, but it's like that. It's I think it's a very nice result. And of course, we have also LP bounds, so we can derive directly from this LP bound this type of uniform exponential concentration models. Okay, that's finished.
Questions?
You are making an analogy with loss of equation in fluid dynamics. In physics, loss equation first approximation, second approximation is Landau equations, and some further equations are important too. What will be for you an analogy of high order equations?
In that case?
Yes.
No, in fact, you are talking about high order equation because of the Navier-Stokes equations. But the Navier-Stokes equation is not so trivial to approximate or to study. In that case, it's not the case. We have a Feynman-Kac model or filtering problem, and we solve directly this problem. There is no first or second or any order approximation. So we take that, we have a nonlinear Markov chain, and that's it. The point is, in your question, is how to find a diffusion or some kind of order approximation of the Navier-Stokes equation that gives exactly the Navier-Stokes equation, which is, I think, another question. Here is another model.
More questions?
Just a naive question of definitions. You talk about this nonlinear Markov chain. Am I right in thinking that you can visualize that as a Markov chain in this space of laws?
Oh, okay. In filtering, of course, these are random Markov chains, in a sense that.
And if I lifted it up into the distribution space, the space of measures, it would be a Markov chain in that space.
This one? You're talking what?
I
This one is direct because it's a Markov chain. I mean, the normalized measures, which are written, okay, there. The first line, if I look at the evolution in time, I end up with that. I end up with a nonlinear dynamical system in the space of measures.
Yeah, okay. So, yeah.
So this
So
one,
when you're talking about a nonlinear Markov process,
Is this
I
one?
think you can visualize it as being in one-to-one correspondence with a Markov chain of measures.
yes.
More questions? No. Thank our speaker again.